Welcome back. This is an Aleks training video on predicting the qualitative acid-base properties of salts. Okay, pretty involved here. The basic teaching here, the basic lesson to learn is that if you have a strong acid, what that means is that acid really wants to give away its hydrogen. If it completely dissociates, then it wants to give away its hydrogen. If you have a weak acid, it doesn't want to give away its hydrogen, okay? Because it's weak. It's keeping as molecules. It doesn't completely dissociate. Now, if I give away a hydrogen, what's left over in that molecule is its conjugate base. So if I have a very strong acid, then it wants to throw the hydrogen away. Then I'm going to have a very weak base that wants to catch that hydrogen or receive that hydrogen. The more likely it is to give it away, the less likely it is to grab it back. So the conjugate base of a strong acid is hardly any kind of a base, because the stronger the acid, the wimpier the base. So let's say you have a weak acid. The stronger the weak acid, the less strong the conjugate base. The more likely it is to throw the hydrogen away, the less likely it is to catch it back, because it wanted to give it away in the first place. All right, so along the edge here, I've got some statements that you have to be able to kind of put your brain around. So let's look at these. First one says the conjugate base of a weak acid acts as a weak base. Okay, I misspelled weak. Acts as a weak base. So the conjugate base of a weak acid acts as a weak base. All right, just accept that. If you have a weak acid and you give away the H, it's also going to be a weak base. Okay, so think about water. Water is a weak acid. So most water stays H2O, but some water will break down. It autoionizes, breaks down into H plus and hydroxide. Okay, so that means that water can act as an acid, but also water can receive a proton and become hydronium. So the conjugate base of a weak acid is a weak base, and it works the same way the other side around. The conjugate acid of a weak base is a weak acid. So if you have something that's weak and you throw the hydrogen away or you receive the hydrogen, whichever way, its conjugate will also be weak. Okay, so that's the first thing to kind of memorize or write down or something. Then, to answer this question, which we'll look at in a second, the weaker the weak acid, the stronger its conjugate base. Okay, so the less likely I am to throw away the hydrogen, the more likely I am to catch the hydrogen because I want it. The more likely I am to throw the hydrogen away, the less likely I am to catch it. Okay, so that's the idea that the weaker the weak acid, the stronger its conjugate base. Okay, and then the last one, the conjugates of strong acids or strong bases don't do anything to the pH. So if they completely break apart, then they never want to catch, because every time they're together, they would just break apart again. So strong acids, strong bases that completely dissociate, its conjugate are not going to be acids or bases. They're not going to be anything. They're nothing. So going over it again, if you have a weak acid, the base left over when you throw the hydrogen is also weak. That's going to be a weak base. If you have a weak base and you receive a hydrogen and you become a conjugate acid, that acid is also going to be weak. Okay, so the conjugates of weak is weak. That's the first thing to remember. Then, here's the next thing. The weaker the acid, the stronger its conjugate. The weaker the base, the stronger its conjugate. And then the final thing is that if you have a strong acid or strong base, its conjugate doesn't affect pH at all. Okay, so in this particular problem, you've got some case of A's. Now remember, the case of A tells you if it's more likely to produce products or not. So if you have a very little case of A, you're going to have lots and lots of reactants, which means it's weak. They didn't break apart. They kept together. So you're looking for low numbers here. So, and I have them. You've got hydrofluoric acid, 6.8 times 10 to the negative 4. So that's showing it's a weak acid. 3 times 10 to the negative 8, that's a weak acid. And then you've got some bases. 1.7 to the 10 to the negative 9, that's a weak base. 6.4 times 10 to the negative 4, that's a weak base. All right. Now, which one is weaker? Let's look at the acid. Which one is more a smaller case of A? That would be the weaker of the acids. Well, HClO is weaker. So this over here says the weaker the acid, the stronger its conjugate base. All right, so I need to come over here and make some comments. So it says that the HClO is weaker. So I'm going to just write that here. The HClO is weaker. That means that's a weaker acid, so it's a stronger base. Which one is the weak base? Let's come back and look at the base. Which one is the lowest base? So the lowest case of B is 1.7 times 10 to the negative 9. So it's the pyridine. It's going to be the weakest. Okay, so this is going to be the weakest or weaker. So it's going to be the stronger acid. Okay. Now, just remind yourself what strong means. If it's stronger, it breaks apart more. If an acid breaks apart more, it's going to make more hydroniums. And if it makes more hydroniums, it's going to have a lower pH. The more hydroniums you have, the more that number negative exponent is bigger and bigger and bigger, the lower your pH, the more acidic it is. All right, so of these two acids, or let's look at the first two. Of these two acids, HF and HClO, okay, their conjugates are going to be weak base and stronger base. So which one's going to have a higher pH? The stronger base is going to be more towards 14. So it will have the higher pH. And this one will have the lower pH of the bases. What about the acids? Okay, so let's look at the acids. You've got so you've got the C5H5N is weaker, so that's going to be the stronger acid. The stronger acid is going to have the lower pH, and the stronger acid is going to have the lower pH, and then the one that's not stronger is going to have the higher pH. And then what happens when you have the conjugate of a strong acid or a conjugate of a strong base? It's going to be neutral. It'll be towards 7. Now rank them in pH. Now you have to do your acids first. Okay, you would do your acids first. So what's that going to look like? Your lowest pH is going to be this one. And then we need the next highest or higher pH, which is also an acid. It'll be this one. Then you need neutral, which is 7. It'll be this one. Then you need the lower base. Base has higher pH than acid and higher than neutral, so it would be this one. And then the very highest pH would be your strongest base. It would be this one. Okay, now they're not giving you 5, they're only going to give you 4, so one of these is not here. So what are they giving you? So the first one is, so let's look at it, C2H5NH3 plus. So that will be here. Okay, so that would be R negative 2 or R2. Let's just write it here. This was R2. That doesn't count anyway because it's not in the box. It's just for yourself. Okay, what's the next one? NaF. NaF. So we have that as 4. NaF was 4 right here, F. And then what about KClO? ClO we had as 5. And then the last one, KNO3, we had that one as 3. All right, so we don't have a 1. So our lowest, this is going to be lowest. This will be our 1, which is lowest. Okay. Then 3 is what we have as 3. That's the next one. That will be 2. And then what we have as 4 is the next one. That will be 3. And what we have as 5 will be 4. And it's the highest. So lots to get your mind around here. Lots. But I'll help you if I can.